Okay, welcome back. This is Mr. Hassan's Maths channel, and I'm now going to answer question number 7, part A, from the P4, from the C4 Solomon collection. I'm going to answer the whole of the question actually. From the C4 Solomon, H is from the Solomon collection of papers, and it's called C4. Well, now we call it P4. And the question is from my end of topic worksheet, which I give to my students for P4, which is number 3, parametric equations. It's question 4 from that worksheet, question 7 from the Solomon paper H. Now, a curve has parametric equations x equals t times, in brackets, t minus 1, and y equals 4t over 1 minus t, and t is not equal to 1, of course, otherwise this part will become undefined. We've got to find dy dx in terms of t. So here we have what's called a parametric equation. What we're used to seeing is a Cartesian equation where you have y as some function of x. What we have here is x as some function of t, and y also as some function of this third parameter t, hence called a parametric equation, and combined together they give us the curve that we need to define. Okay, so y equals f of x is Cartesian, and this is parametric. So there's, for us to find dy dx, we could change this into a Cartesian form and then find dy dx as we normally would. However, it's normally a lot easier to find dy dx by using the chain rule. Okay, so to use the chain rule, it's normally not so easy to change it into Cartesian form. Well, it's possible, but it's normally easier to just use what's called the chain rule to do this. So the chain rule is basically where our objective is to find dy dx, as they asked us to do. So what we can do is we can find dy dt and multiply that by dt dx, and that leaves us with dy dx. So we got to take our function y equals 4t over 1 minus t, and x equals t, I'll just expand this, t squared minus t, and I can find the dy dt and dx dt. Okay, so I'll find dx dt and then use this reciprocal to multiply with dy dt. That will be dx dt will be, dx dt is going to be 2t minus 1. So that means dt dx is going to be the reciprocal of that. That's all. It's very simple. That's going to be 1 over 2t minus 1. Now, I left this second because here we have y equals 4t over 1 minus t. Now, for me to differentiate that to find dy dt, I have to use the quotient rule here because I have a quotient of two separate functions. I could write this as 4t times 1 minus t to the power of minus 1 and then use the product rule, but there's a quotient here, so it's fine. So let me call this u and call this v. Now the quotient rule is actually quoted to us in the formula book, and you could look it up and see. I mean, once you've got used to it, then it's not so necessary to look it up. So I'll just show you exactly how I set it out. I always put my u here, which is the numerator. For when you got the quotient rule, that has to be the u, and this has to be the v, and the v is going to be 1 minus t. I find the differential of u, which is going to be 4, and I find the differential of v, okay, which is going to be minus 1. And then I use the quotient rule, so I always start from this side. I multiply these across, starting from this side, so I'm going to have 4 times 1 minus t, then I have minus, and then these two are multiplied, so it's minus 4t times minus 1, which is minus 4t, all over, and then I take v and square it, so it's 1 minus t all squared. So that's your dy dt. Okay, so if you simplify that, that gives us 4 minus 4t, 4 minus 4 times t plus 4 times t over 1 minus t all squared. So we can say dy dt is equal to, they cancel out the minus 4t and the plus 4t, you're left with 4 over, in brackets, 1 minus t all squared. So we got dy dt and we got dt dx. So we can say dy dx is equal to dy dt, which is 4 over 1 minus t squared, times dt dx, which is 1 over 2t minus 1. So we can just simplify that to say dy dx equals 4 over the product of 1 minus t all squared times 2t minus 1. And there's our answer for part A. That is an expression of dy dx in terms of t. Okay, in terms of t. All right, and in fact, if we had changed this into Cartesian form and then found dy dx, we wouldn't have got dy dx in terms of t. So that is not really an option. We could have then used some sort of substitution to find it in terms of t, but that would be a very long-winded way of doing it. So it's much easier to use the chain rule, and it's, that will give us the answer as required in the question. Okay, so that's dy dx. Now part B says the point P on the curve has a parameter t minus 1. Show that the tangent to the curve at P has this equation x plus 3y plus 4 equals 0. So now, a tangent to a curve, okay, a tangent to a curve has the same gradient of the curve at the point at which it's a tangent to it. So this is the tangent. That's not going to work, is it? If that's the curve, and the tangent is like this, for example, okay, then the tangent has the same gradient of the curve at the point at which it hits the curve. Okay, so supposing this is the tangent to the curve, at that point they have the same gradient. Okay, so if I want to find the equation of the tangent to the curve, I need two things. I need to have the gradient of the tangent at the point P, and I also need I need the coordinates of the point P. I need the x and y coordinates of point P, okay, and then I can find the gradient of I can show that the equation of the tangent is this. I can find the equation of the tangent if I have those two things. Now, as for the gradient of the point P, the gradient at the point P is dy dx. Okay, we know the gradient function for this curve is 4 over 1 minus t all squared times 2t minus 1. And we know at P, as they told us, t is equal to minus 1. Okay, at P, t is equal to minus 1. So that means the gradient of the curve at P is going to be 4 over, so this is the gradient of the curve, which means it's the gradient of the tangent at P. Okay, so the gradient of the tangent, so I'll just write that as mt, the gradient of the tangent at P, you see, the gradient of the tangent to the curve at P is going to be 4 over 1 minus 1, so it's 1 plus 1 squared times 2 times minus 1 minus 1. That's going to be 4 over, that's 2 squared, which is 4 times, and you're going to have minus 3 minus 2 minus 1, which is minus 3. So they cancel, you're left with minus 1 over 3. So we know the gradient of the tangent is minus 1/3. Now we've got to find the x coordinate of P and the y coordinate of P. So I know that x is equal to, as we know from the equation above, x is equal to t times t minus 1. So x is equal to t times t minus 1, t times t minus 1, and we know that y is equal to 4t over 1 minus t. So y is equal to 4t over 1 minus t. So we can say when t equals minus 1, which is where at P, when t equals minus 1, we can find the x and y coordinates at P. So x is going to be minus 1 times minus 1 minus 1, which is minus 1 times minus 2, which is 2. And y is equal to 4 times minus 1 over 1 minus minus 1, which is minus 4 over 2, which is minus 2. Okay, that's minus 4 over 2, which is minus 2. So we can say the coordinates of P, therefore, are 2 minus 2, and the gradient of the tangent at P is equal to minus 1/3. So now we can use y minus y1 equals m times x minus x1 to find the equation in the form in fact we have to give that exact x plus 3y plus 4 equals 0. So we have y minus minus 2, y minus minus 2, so it's y minus y1 equals m, which is minus 1/3, times x minus x1, which is x minus 2. So you're left with y plus 2 equals minus 1/3 times x minus 2. I'm going to multiply both sides by 3, in which case I'm going to get 3y plus 6 equals minus x minus 2. So you have 3y plus 6 equals minus x plus 2. Now we want to bring everything onto one side, make the x positive. So if you add x to both sides, you're going to have x plus 3y, and you're going to have 6 minus 2, which is plus 4 equals 0. And that's exactly what we had to show. X plus 3y plus 4 equals 0. So there's part B done, showing that the tangent to the curve at P has that particular value. Okay, so now part C. Part C says the tangent to the curve at P meets the curve again at the point Q. Find the coordinates of Q. Okay, so we worked out the coordinates of P were 2, minus 2. Or was it minus 2, 2? Let me just make sure. P, the coordinates of P was 2 minus 2. Okay, so we know that much. And we know the equation of the curve parametrically. We also know the tangent to the curve. So now for part C, it says find the coordinates of the point where this line meets the curve again. All right, so you got a curve that curves maybe like this and then like this again. That's the tangent at one particular point, and that tangent hits the curve again at another point. Okay, so we got to find that other point. So basically what we've got to do is we've got to solve these two equations, these equations simultaneously. I've got to find where these intersect. I already know that they have one solution, which is going to be a repeated route at the point where the tangent hits the curve. That's one thing I know, and I also know that they're going to meet again somewhere else. So how do I solve a parametric equation and a Cartesian equation? How can I solve them simultaneously? Well, it's pretty easy actually, because all I have to do is use substitution. I know that if I substitute, instead of x, t times t minus 1 in here, and instead of y, 4t over 1 minus t in here, I'll have an equation with just t in it. And if I solve that, I'll find the solutions of where this parametric equation intersects this Cartesian equation. Okay, so all I have to do is I've got x plus 3y plus 4 equals 0. So I'm going to replace the x with t times t minus 1 and replace the y with 4t over 1 minus t, and I've got plus 4 there equals 0. So if I solve this equation for t now, I will get the values of t where these intersect, and then I can use that to find what q is. So this is going to give me t squared minus t plus 12t over 1 minus t. I'll just put equals minus 4. All right, just get rid of that from this side for now. And I can actually in fact leave it here because it doesn't really affect anything. Just leave it here. And then what I can do is I want to get rid of the denominator. So I can multiply the whole thing by 1 minus t. That gets rid of the denominator. So I'll multiply this by 1 minus t, the whole thing. So I'll have 1 minus t times, you could say t squared minus t. And I'll have 1 minus t times 12t, which will give me 12t. I'll have 4 times 1 minus t, and that's equal to 0. So now that will give me, if I expand this, it's going to give me t squared minus t cubed plus t squared, right? That's going to give me, yeah, that's going to be giving me, t squared minus t cubed plus t squared. That's right. I've got plus 12t plus 4 minus 4t equals 0. Let's just bring everything correct together. We've got minus t cubed. Then we've got t squared plus t squared. That's plus 2t squared. And then we got minus t plus 12t minus 4t. So that's 12t minus 5t, which is plus 7t. And you got plus 4 equals 0. Let me make the t cubed term positive just to make it a bit neater. So that's t cubed minus 2t squared minus 7t minus 4 equals 0. So I have this cubic equation which I have to try to solve. Now what I know already, okay, is that at p t equals minus 1. At p t equals minus 1. All right, we know that already from what we learnt in this question. It says the point P has parameter t equals minus 1. So I know already that t plus 1 is a solution to this equation. In fact, because at P there's a tangent to the curve, I know that there is a repeated route. So t plus 1 squared is in fact a root of this equation, because when there's a repeated root, there's a tangent. Okay, that's where the curve touches the line, doesn't pass through it. Okay, so I know that at P, okay, so I can say at P, okay, when t equals minus 1, there is a repeated root, because it's a tangent, a repeated root. Therefore, t plus 1, okay, squared is going to be one of the factors. T equals minus 1 is a repeated root, therefore t plus 1 squared, there's two factors to this. So what I can do to make this life much easier for myself, I can say that this t cubed minus 2t squared minus 7t minus 4 is equal to t plus 1 squared times, you can say t, I know there's going to be a t, plus, you can call it a, okay, you know, there's going to be some, I'll just call it k, save some confusion, t plus k, right? So I know, for example, if I expand this, I'm going to get a 1 at the end, and that 1 has to multiply with this, and it's going to give me minus 4. So therefore, I can say that this is going to be t plus 1 squared times t plus 4. Okay, so I know that the other part, where at q, I know that t must equal minus 4. Okay, because I know this must give me, sorry, this has to be minus 4, not plus 4. Minus 4, sorry about that. So that means t must be plus 4, because I have to get a minus 4 when I multiply this out, and this is going to give me a 1 when I expand it. 1 times minus 4 is minus 4, and we can check. If I expand this, I'll have t minus 4 times t squared plus 2t plus 1. This is going to give me t cubed plus 2t squared plus t. Then you're going to have a minus 4t squared. You're going to have minus 8t. You're going to have minus 4. So it should give us back to this. So you got t cubed, and you're going to have 2t squared minus 4t squared, which is minus 2t squared, t minus 8t, which is minus 7t, and minus 4. Is that the same as this? T cubed minus 2t squared minus 7t minus 4. You see, it's exactly the same as this. So we know for sure that this is one of the factors. So that means that at q, t must be equal to 4. At q, t is equal to 4. So now I can find the coordinates of t, of q, sorry. Okay, so knowing the fact that it was a repeated root helped us a lot in this question to make the next part of the question really easy. Otherwise, you'd have to use some sort of algebraic long division. Like if I had not realized it's a repeated root, I would have said t plus 1 is a factor. Then I could have solved it by doing t plus 1 and long division and find the other factor, then factorize it, and I'll end up with, t minus 4 and t plus 1. And then I'll say, oh, t plus 1 squared. Then I'll realize, oh, it's actually a repeated factor. Okay, so therefore, knowing that when there's a tangent to a curve, that point is actually a repeated root, that will help you a lot. Okay, so here we know that t is equal to 4, so we can go back to our original equation. I'll just bring this down here. Our original parametric equation. Let's bring it down so we can see what's happening. Okay, so now I can find what the coordinates of q are by just simply putting t as 4. So when at q, you're going to say x is equal to 4 times 4 minus 1, which is equal to 4 times 3, which is 12, and y is equal to 4 times 4 over 1 minus 4, which is 16 over minus 3. Yeah, t is equal to 4, right? So 16 over minus 3. So the coordinates of q are 12 for x and minus 16 over 3 for y. And there's the answer to that question. Okay, so that's why it's worth 7 marks. But it's very helpful to realize we have a repeated root of t plus 1. And that's what helps us find the other root easily. Okay, so I hope that was clear. What's happened here? Everything's moved down. 1 second. Yeah, okay. So there we have the answer to that question. All right, so I hope that was clear. This was a question all about parametric equations from P4. The other questions that I answered from this Solomon H paper, you will find them in this playlist that will appear over here. Other questions that are to do with parametric equations from P4, you'll find them in this playlist. You can subscribe to my channel by clicking on this link, and at the top of the page in the top right here you'll have a card taking you to a P4 paper that I've answered. Thank you for watching. I hope you understood, and see you soon.